So in this lecture now, we're going to finish off chapter 3 by, I know we already looked at it briefly at the end of the series chapter, but we're going to look again at this technique of finding partial fraction expansions. Now we'll go with a few examples. It's an important technique and is very useful in certain situations for dealing with so-called rational functions. But just remind you, as I announced yesterday, very soon, I think at the beginning of next week, I'll put up a mock test for the class test that you'll be taking. And so next week is week 10. In week 11, we'll do revision activities. So if you've got any particular topics that you'd like me to, include in those revision sessions, or any particular questions, be they questions from my notes or questions from some of my extra tutorial sheet questions, and that you'd like me to include in those revision sessions in week 11, please do send me an email with those requests, and I'll do my best to accommodate any that I receive. So that's coming up in the next couple of weeks. Next week, there's a small section at the end of this, chapter 3, after the exercises on cardinality and infinite sets. It's a bit more of a light-hearted interest topic. It didn't fully come out. I'm not quite sure what happened. I think I haven't finished writing that part of the notes already. So my lecture next week will be on that topic. Questions for now? Anybody got any questions at the moment? Everybody okay? Okay. This probably won't take too long, this particular lecture, so there might be time at the end as well if any of you've got individual questions or anything you want to come up and ask. Okay, so what we're looking at is on page 29 in the notes, this section on partial fractions. So what we're dealing with here is is a technique that can be used when we're trying to do various operations on so-called rational functions. So what a rational function is, what we mean by that is a quotient of polynomials. So a rational function R is a function P over Q, where P and Q are themselves functions where they're polynomial functions. All these functions I'm mentioning, we consider them as functions from the real numbers to the real numbers. Polynomial function is just some function of a single variable x, say, and it's a sum of various powers of x, and you can have various coefficients multiplying each of those powers of x. Now, so normally, So we imagine ourselves in a situation where we're faced with a certain rational function. Here's an example of one, x over x cubed plus x squared is 2x minus 4. Now that's a particularly nice form for the rational function, nice single fraction. But for certain purposes, it's not the easiest thing to handle. For instance, if you had to integrate that function, it's kind of tricky to decide what the integral of that is going to be. And there are a number of other instances where you're treating expressions like this, where that single fraction form isn't necessarily the best kind of thing to have. So what partial fraction expansions allow you to do is to get an alternative expression for the same function. So this will be this final one on the right. Okay, it's a longer expression. It's now a sum of 3 different fractions. And then maybe got awkward, numerators there, fractions of ninths, but they're still constants. But what has simplified, or what has been made slightly easier there is, although it's a sum of 3 different functions, but 3 different fractions, but the fractions themselves are simpler in that the degrees of the numerator are smaller individually. Previously, we had a degree 3 numerator, cubic, whereas now we either have degree 1 polynomials, x plus 2, x plus 1, or in the middle fraction, a quadratic polynomial. So what has simplified is the nature of the individual rational functions. Now, there's a mathematical, there's a result about polynomials which lies behind what we're doing here. Now, we're not going to prove this result by any means, but we will just look at it. And this is a result about polynomial factorization. So it deals with polynomials over the real numbers. And when we say polynomials over the real numbers, we mean that the coefficients of the polynomial, these numbers an minus 1, an minus 2, etc., coefficient a naught, these are real numbers. Okay? Real numbers. And the theorem says that such polynomials with real coefficients, you can always factorize them. You can always break them down into a product of simpler polynomials. And the different factors in the product that you can factorize it down into, they are either of the form, this first form here, some power of a linear factor, an order 1 factor, some power of a factor x minus a, x minus some constant. Now that might itself be raised to a power n in factorization. And sometimes the other type of factor you might have a quadratic factor, x squared plus ax plus b. So you can't necessarily factorize every real polynomial down into linear factors, just factors of the form x minus a. Sometimes we encounter so-called irreducible quadratic polynomials. Polynomials x squared plus ax plus b, which cannot be written as the product of two order 1 polynomials. Okay. But everything else can be broken down. There's no such thing as an irreducible cubic polynomial over the real numbers. And there's no such thing as an irreducible order 4 polynomial over the real numbers. You will always be able to break down an order 4 polynomial either into a product of two irreducible quadratics or into an order 1 factor times a cubic factor and so on. Okay. So every real polynomial does ultimately break down into a product of factors, each of which are either order 1 like this one or order 2. So that's the result that's kind of lying in the background. And the method of partial fractions, we can give a general description which kind of covers all possible cases here. We'll get on to doing some examples shortly. So we suppose P over Q is a rational function. So the denominator part, Q of x, is a polynomial. And we suppose that we're able to factorize the denominator polynomial. Okay? Now that might be difficult in practice if it's a high degree polynomial. But assuming that we can factorize it, and we can know what the factorization is, then we can build up a partial fraction expansion for R as follows. We're going to get a bunch of fractions corresponding to each different factor of the denominator polynomial Q. So there's two cases to deal with, to describe when the factors look like x minus a, or when they look like x squared plus ax plus b. Okay. So when the factor looks like x squared plus ax plus b, when it's one of these irreducible quadratic factors, then depending on the power n, you get a bunch of fractions, all which have denominator the same quadratic, x squared plus ax plus b, raised to an increasing power. Okay. So if you have x squared plus ax plus b to the power n, that's a factor of q of x, then you've got n different fractions, 1 over x squared plus ax plus b, 1 over x squared plus ax plus b squared, 1 over the polynomial cube, etc., all the way up to 1 over the polynomial, the quadratic polynomial to the power n. And each of the numerators is an order 1 polynomial. So a constant times x plus another constant. Okay. Now for the moment, these constants up here, these coefficients, alpha 1, beta 1, alpha 2, beta 2, all the way up to alpha and beta, and these are unknown to us at the moment. Okay. The task is to find these a little later on. But the theory says that in the partial fraction expansion of R, we will see this bunch of fractions, okay, coming from this factor here, x squared plus ax plus b to the power n, coming from that factor of the polynomial q. The simpler type of factors, the ones which are x minus a to the power n, they yield a similar collection of fractions, okay, all over that same factor, x minus a to some power. You got over x minus a squared, etc., all the way up as far as x minus a to the power n, whatever the value of n is. But this time the numerators are just simple constants. So there's no x term in the numerator for these. Okay. You just have some collection, alpha 1, alpha 2, up to alpha n, just some bunch of unknown constants. So these alphas appearing over the x minus a will not, of course, be the same as these alphas here. I'll just use the same letter again. Okay. So each irreducible quadratic factor you have here generates a bunch of these, and many of them is dictated by whatever the value of the exponent is. And each linear factor x minus a of q yields a bunch of these, the number of them dictated by whatever the exponent n. Okay. Now, it may be we need to have some extra terms. If it's the case that the degree of the numerator polynomial p is less than the degree of the numerator polynomial of the denominator polynomial q, so if the degree at the top of the fraction is less than the degree at the bottom, then that's all you have. You just have these fractional terms. However, if the degree of the numerator polynomial p is equal to or exceeds the degree of the denominator polynomial q, then you've got some extra terms in the partial fraction expansion. These are not fraction terms, these are just straightforward polynomial terms in x. Okay? N is the amount by which the degree of p exceeds q. So n might be 0 if the degree of p is equal to q, or some number bigger than 0 if the degree of p is actually bigger than the degree of q. So n is the difference in degrees. So whatever n is, you will get this bunch of terms as well added into the partial fraction expansion. Okay? And again, these unknown or these yet to be determined coefficients, written in there as lambdas. So lambda naught is a constant coefficient, it's lambda 1x, etc., all the way up to lambda m times x to the power n. And you got to add all these different terms together, just this big long expression, okay, which in one way is much more complicated than the original p over q, but in another way is simpler because each individual term in the sum is a simpler type of function because the degree of the denominators, if they're there at all, is less than the degree of the denominator of the original fraction p over q. So they're each term in your big long sum will be simpler type. And then you have to go through a process to determine all these unknown coefficients. Okay? And we do that by taking your big long symbolic expression with all these unknown coefficients in the numerator and mushing them all together back into a single fraction, putting them all over the common denominator q. Product of all the q will be a common multiple of all the denominators you have. So you add all the fractions together back into this single fraction. But this time you're adding all the numerators which contain all the unknown constants. So you'll get some big long numerator polynomial which has all these constants in it. And you compare that back to the original numerator polynomial p, all the way back up here, the original. So by comparing this new numerator with all these unknown constants back to the original numerator p, those two polynomials will have to be the same. Two polynomials can only be the same if they've got corresponding coefficients are the same, meaning corresponding coefficients of equal powers of x. If those coefficients are each the same as each other on either side of the equation. And so that will give you a bunch of equations in the unknown coefficients, which, using your Gaussian elimination technique from linear algebra, you know you'll be able to solve. Okay. It may be long and laborious. Of course, if it's long and laborious, you don't do it by hand, you give it to a computer. Computer does it. But we know that any system of linear equations, if it has a solution, you can find that solution algorithmically using Gaussian elimination. So in one go, that's the description of the general method. What we need to do now is to illustrate that with a few examples. So you can see it working in practice and relate what we're doing in the particular example back to the general description. Okay. So there's a couple of examples in the notes here which I'd like to talk through in the on the screen for you. And please, if you want to stop me at any point and ask questions as we go, please feel free to do that. These are examples 3.7. Good. So the first one, we're looking at the polynomial 3x plus 1 all over x cubed minus 3x plus 2. Okay, so this is a good candidate for finding a partial fraction expansion of. Okay, because the denominator polynomial is a cubic, so we know we ought to be able to simplify that by factorizing it into a product of lower degree polynomials. And indeed we can. We can spot that that factorizes into x minus 1 squared over x plus 2. Now these example ones have been chosen so that the roots of the polynomials aren't that hard to find and they're relatively easy to handle. Okay. So here you can see the denominator polynomial is factorized fully down into linear factors. X minus 1 with a multiplicity of 2 to the power of 2, and a factor x plus 2. So following the general method, the partial fraction expansion of this is going to look like some unknown constant a over x minus 1 plus another unknown constant b over x minus 1 all squared plus a third unknown constant c over x plus 2. Okay, that's all well and good. The theory tells us we should be able to represent this rational function like this. There are no single polynomial terms in x to include because the degree of the numerator is less than the degree of the denominator. Okay, so there's none of those lambda naughts or lambda 1x, etc. to include here. But we see our constants to be determined. Okay. We don't know what they are, but we have a process that we can go through to find out what values they do have. And that process is to immediately add all the fractions together again to bring them back to the representation as a single fraction over this. Okay. Now I know that the numerator up here must be 3x plus 1. Okay, that's what it's equal to. We've got the same denominator. Okay, but I'm not going to write it as 3x plus 1. Now I'm going to bring through these unknown constants and see how they feature in the numerator. Now, what do we need to multiply by a? Well, a is over the denominator x minus 1. So in order to keep it over x minus 1, I have to multiply it by x minus 1 times x plus 2. Okay, so that x minus 1 and x plus 2 cancels with this below, and you're just left with x minus 1 in the denominator. And then you're going to add b. But b is over x minus 1 all squared, so you have to multiply that by x plus 2, so that it is still over b over x minus 1 all squared. And lastly, we add on c. And c is over x plus 2, so if you're putting that over this common denominator, you have to multiply it by x minus 1 all squared. Okay?
Excuse me, I think there you meant x minus 1. B over x minus 1 in the middle. Second line in the middle.
No, because when I see b is over in the middle line, b is over x minus 1 all squared.
Why?
Up here. Yeah.
Yes. Why is it squared?
Why isn't what squared?
Because you have x minus 1 under a.
But see, I've got a over x minus 1 here. So in order to get it ready to add all the fractions together, I have to put them all over the same denominator, x minus 1 all squared times x plus 2. So I need to multiply the numerator of a by x minus 1 times x plus 2. Yeah? So I've just done a separate sheet. So if you have a over x minus 1, what I'm saying is this is a times x minus 1 times x plus 2 all over x minus 1 squared times x plus 2. Okay? And that because these cancel off to leave just x minus 1 in the denominator. And then similarly, b over x minus 1 all squared. I want to write that over the same denominator. So the x minus 1 squared is already there, so I just need to multiply b by x plus 2 to cancel off that. Yeah. And then lastly, the c over x plus 2. I want to write that over the same denominator. So the c must get multiplied by x minus 1 all squared. So now I have these three fractions and they're all over the same denominator, so I can just simply add them, adding the different numerators. Is that okay?
My question wasn't.
Oh, sorry. What's the question?
No, my question is that we don't need this power to here, or maybe I'm wrong.
Oh no, we do. No, we do need that. Sorry.
I think we do.
So we do need the, well, I mean, it may turn out that b is equal to 0. It may come out in the wash that b is equal to 0, but I do need this b over x minus 1 squared because x minus 1 is raised to the power 2 then. If it was just x minus 1 in the denominator, then this b wouldn't be needed. And it'd be just something over x minus 1, something over x plus 2. If that square wasn't there.
Oh, because they multiplied.
Yeah, but because the square is there, you need this extra term in the partial fraction expansion. Okay, so it's good to clear that up. So continuing on, what I want to do now, see, this fraction is the same as this fraction. They both have the same denominator, so the numerators must be the same. So I want to compare the numerators. But this numerator here is in standard polynomial form, something times x plus a constant. This one is a bit mixed up, because x's all over the place. So you want to collect together all the terms and represent this new numerator in the standard polynomial way. Okay? So there'll be a bunch of x squareds here. There's an a times an x squared, so there's x squared there when you multiply this out. There's no b times an x squared, but there is a c times an x squared, so you get an x squared there. So in total, multiplying x squared, you've got a plus c. Then you look for your x's. So are there x's coming out of here? Yeah, there's 2 times x minus x. So in total, there's a x term coming out of here, but it gets multiplied by a. Are there any x's coming from the middle term? Yeah, there's a b times x. Are there any x's here? Yeah, there's a minus 2 times x, which then gets multiplied by c. So it's a minus 2c x. You were looking doubtful just there in the middle? Did you have a... Have I gone wrong? Or I'm not, I'm just trying to draw out questions. Okay. Well, I'll make reference back to that different ways some of you might have seen before in a moment. So there's the x squared term, the x term. I'm now looking for a constant term. Is there a constant coming from here? Yeah, there's a -2 there. And it gets multiplied by a. So it's a -2a. Is there a constant from here? Yeah, there's a 2b. Finish the joke. Or not too big, yep. And there's a +1 here, which gets multiplied by c. Okay? So when you multiply this whole numerator out, this is what you get in standard polynomial form. Something times x squared, something times x, plus a constant. Okay? Now I can make the comparison back to this original numerator 3x plus 1. Comparing the numerators in the first and last fractions. Okay, the first fraction up here, the last one, big one down here, they've got the same denominator, so the numerators must be equal. The numerator polynomials must be equal. I'll just pause there because people are still figuring out that multiplication there. Is everybody okay with how I multiplied it out there? Yeah, so what I'm doing is I'm avoiding that subbing in method because I've seen people go wrong with it before. Okay, well, I may as well explain it now. So some of you may have seen a method before where at this stage here, okay, you substitute in various values of x, like x equals 1, because that will rub out this, and x equals -2, and so on. That isn't incorrect, but I have seen people go wrong with it. And where they go wrong is if you haven't formed the original partial fraction expansion correctly, let's say you skipped out this middle term here, then you do reach, you miss out that middle term, you multiply it together, you get this. You can still apply that cover-up rule, and you can still seem to obtain values for a and c, and then you kind of make the declaration, well, this is the partial fraction expansion, but it's incorrect because you didn't include the full information up here. Whereas this method, if you do leave something out up here, and you follow this method through and then compare the polynomials, you will reach a contradiction if you make an earlier error. So I'm not saying don't use that cover-up method. It's okay, but just be careful when you do, because especially when the partial fraction expansion gets long and there's many terms in it, and it can give you a false sense of confidence because the cover-up rule will always provide values for whatever constants you have. And then you may think you've reached the correct expression at the end. But because you missed out some parts of the proper expansion, it doesn't tell you that, okay? Whereas this method, because you're doing a strict comparison of the polynomials, this method will always yield the correct result in that if you have left something out, it will tell you, and it'll be obvious that there's a contradiction. Okay. Other questions?
Could we expand it all and then take the AC out like that?
Yeah, I mean that's what I was just doing in one leap. Yeah. So I decided to look for x squareds first. So just see if there's any x squareds coming from here. Yeah, there's an a times x squared. See if there's x squareds coming from here. No, there isn't. Your way is just to focus on all of the bits of this, then all of the bits of that, and then grab a quit. Either way is fine. Yeah, either way is fine. Okay, so what I wrote down there is we now have to compare the numerators. The numerators must be equal. okay, because the denominators are equal. Remember, if you have two fractions equal to one another, you can't just claim the numerators are equal because the denominators might be different. But here the denominators are the same, so the numerators must be the same. And the numerators are polynomials, and there's a basic principle of polynomial equality that polynomial functions, two polynomial functions, can only be equal as functions if their corresponding coefficients are equal. So this implies if I look at the x squared coefficient, the x squared coefficient down here is a plus b. And what's the x squared coefficient in 3x plus 1? Well, there isn't an x squared there, but it does have a coefficient. It has a coefficient of 0, okay? Because there is no x squared. Next, I look at the x's. The coefficient down here is a plus b minus 2c. That must equal the x coefficient in the original polynomial, which is a 3. And lastly, the constant, x to the power 0. The constant coefficient down here is minus 2a plus 2b plus c. And that must equal the constant coefficient in the polynomial above, which is 1. So what we get is a system of equations, system of three equations and three unknowns. So we can always use Gaussian elimination, the row reduction algorithm that you've learned in linear algebra, to provide us the solution to this. Now, whether we go for full-blown Gaussian elimination here or not depends on how complicated this is. We can shortcut it and just look at some quick combinations of these equations, which will hopefully simplify them for us and give us an answer. So I think I'll go for that method here because it's not too big. It's just 3 by 3. So if I just do some quick, appropriate substitutions and combinations, I'll get the answer. So if I, first of all, if I do equation 1 minus equation 2, sorry, 1 minus equation 3. If I do 1 minus equation 3, this gives me 3a minus 2b, and the c's cancel, and that must equal minus 1. And then if I do equation 2 plus 2 times equation 1, that will cancel the c's there as well. So equation 2 plus 2 times equation 1, again I get 3a. Equation 2 plus b. And the c's cancel, and this has to equal 3. Okay, then I can simply subtract these equations from one another. And that will cancel the a's, so I get minus 3b. Minus 1 minus 3 is minus 4. So I've got one of the solutions. B is 4/3. Seems to be. And if b is 4/3, then this one implies that 3a plus 4/3 is 3. So 3a is 9 minus 4, 5/3. So a is 5/9. And then that implies, then if you look at equation 1, that would imply that c is minus 5/9. So, I mean, if the system is in any way too big, and you don't want to end up going round in circles, you can always go for Gaussian elimination, or ideally type it into MATLAB and get MATLAB to solve it for you, but it would have taken me the same amount of time to type it into MATLAB as it did to just quickly do that. Okay. So the required partial fraction expansion then is 3x plus 1. So the a was over x minus 1, so it's 5/9 over x minus 1. B was over x minus 1 all squared. And the c was over x plus 2. You've got to remember to line up the correct coefficients with the correct denominators at the end, of course. So if any questions or queries about that process? Now, as that point you raised in the middle is fine. There is also the cover-up rule that you can do, where you spot substitutions you can do at this stage here, which will knock out all but one of these terms up here, get you some values there. However, as I said, that doesn't detect errors you made along the way. And also, if the form of the numerator here, if there are many, many terms here, sometimes there'll be variables for which there isn't a simple substitution that knocks out everything except one. Okay, so it doesn't always work. So from a conceptual viewpoint, I kind of prefer this method because it will give you the solution, and if you have made a mistake along the way, you'll detect it at this point here. Okay, because the Gaussian elimination process will either fail to give a solution, or you'll seem to find multiple solutions. Of course, you can't have multiple solutions. Okay, so if there is a partial fraction expansion, there is only one over those two denominators. So I think this method is a bit more robust. Okay, there's another example for you to work with there in the notes. It's one where you've got an irreducible quadratic factor in the denominator. But I think I'll leave it there for this evening. There's a few minutes left, so if any of you have individual questions about any part of the course or unit, things you want to check with me, feel free to come up and we can have a chat. Okay.